Good evening, everyone. My name is Pranav, and I am studying in Institute of Aeronautical Engineering, which is also known as IARE BTech CSC AML branch in second semester. Today, I am gonna discuss one of my favorite topic, which is 10 optimization on linear search in data structures. So, coming to the introduction, what is searching means? Searching is the process of locating a specific element inside a data structure, such as an array or list. It is one of the most common and important operations in computer science. There are different searching techniques, such as linear search, binary search, hashing based search. Based on the requirements of the user, they use different types of search. In this presentation, I'm gonna focus on linear search. So, what is linear search? Linear search is the simplest searching algorithm. It checks each element one by one, starting from the list position. The search continues until the element is found or the element list has been checked completely. So, the every search consists its own time complexity in which it has the best case, worst case, and average case. So coming to the linear search, the best case of the time complexity is O of 1 and the worst case is O of n and average case is also O of n. So how does the linear search actually work? This linear search consists of algorithm steps. It starts from index 0 and compare each element with the target. If match, it returns the index. If the end is reached, then it returns -1. Linear search does not require sorted data, which makes it flexible but sometimes insufficient. Important characteristics of this linear search are it works on both sorted and unsorted arrays, does not require any pre-processing, performs sequential comparison. It is also suitable for small data sets array. So the key observation among in linear search is in this first case, it may compare every element in the array. Now, coming to the limitations of the linear search, although it is very simple and easy to do, linear search has drawbacks. It takes longer time for large data sets. The worst case requires checking all elements instead of picking one particular element. Not efficient when frequent searches are required. Performance does not improve automatically with data size. So the main issue with this linear search is linear search follows a fixed sequential approach and does not adapt based on previous searches. It treats every search independently, even if the same element is searched multiple times. Because of this non-adaptive nature, its efficiency does not improve automatically with usage. So, why do we need optimization in linear search, which is a big question? Because after understanding the limitations of linear search, it becomes clear that improvements are necessary, especially when dealing with large data sets or repeated searches. Also, the worst case time complexity remains O of n. We can still reduce unnecessary comparisons and improve practical performance by modifying how the search is performed to give user the best experience. So the optimization mainly focus on reducing extra checks inside the loop, improving average case performance, making repeated searches faster, utilizing data properties like sorting. Even small improvements in comparison operations can significantly improve the performance when the data size becomes large. So this is why optimization techniques are applied to linear search to make it efficient and better for users. So coming to the optimization in linear search is very simple, but it has some performance limitations. Instead of replacing it completely, we can improve it by modifying with its working strategy. These improvements are also called optimizations. Optimizations does not change overall time complexity, but it reduces unnecessary comparisons and improves practical efficiency. In this section, we'll study 10 important optimization techniques used to enhance linear search. The first one is Sentinel linear search. Sentinel linear search is an optimized variation of basic linear search algorithm. It is designed to reduce the number of conditional checks performed during each iteration of the loop. In a normal linear search, every loop iteration performs two checks, whether the index written within the array boundary, whether the current element matches the target value. This repeated boundary checking increases the total number of comparisons, especially for large arrays. So to avoid this, Sentinel linear search is used to reduce the size total number of comparisons. Coming to the second one, it is move to front method. The move to front method is based on the idea that frequently searched elements are likely to be searched again. When an element is found during linear search, it is moved to the first position of the array, and the remaining elements shift one position to the right. For example, if we take an array as 10, 25, 30, 40, 50 elements, and we search for 40, the updated array becomes 40, 10, 25, 30, 50. This makes future searches for 40 faster. Although the time complexity remains same. The average search time improves significantly when repeated searches occur. So this method mainly reduces the time effort. When we search for an element in array, it automatically makes the element at starting position. Even though the worst case time complexity is same. Coming to the third method, which is transposition method. The transposition method is a self-organizing optimization used in linear search. Instead of moving the found element directly to the front, it swaps the element with the one just before it. This gradually moves frequently searched elements towards the beginning over multiple searches without making a large changes to the array. For example, if the array is again 10, 25, 30, 40, 50, and we search for 40, the updated array becomes 10, 25, 40, 30, 50. If 40 is searched again, it will move further forward. Also, the worst time complexity remains same. This method improves average performance in repeated search situations. So, the transposition method is mainly used in repeated search situations. The more you search about a particular element in an array, it moves it forward. Although the worst case time complexity remains the same. Coming to the fourth optimization, which is early termination. It is only for a sorted array. Early termination is used when the array is sorted in an ascending order. In normal linear search, every element is checked even if further elements cannot match the target. In this method, the search stops as soon as the current element becomes greater than the target value, since all following elements will also be larger. For example, if the array is 5, 10, 15, 20, 25, and we search for 12, the search stops at 15 because 15 is greater than 12, although the worst case time velocity remains same. This approach reduces unnecessary comparisons in sorted arrays. So early termination means early elimination of the remaining elements, and only one particular element remains which we want to get it. And fourth is two-way linear search. Two-way linear search improves the basic approach by checking elements from both the beginning and the end of the array at the same time. Instead of moving in one direction, two pointers are used, one starting from the left and one from the right, and both move toward the center until the element is found. For example, if the array is 4, 8, 12, 16, 20, 24, and we search for 20 element, we compare 4 and 24, then 8 and 20, where the element is found. In this also, Although the case time complexity remains same, this method can reduce the number of iterations in practice. So this two-way linear search reduces the number of iteration to make the user best approach. And sixth is loop unrolling. Loop unrolling is an optimization technique where multiple elements are checked in a single loop iteration instead of checking one element at a time. In the normal linear search, the loop compares one element per iteration. In loop unrolling, the algorithm may compare two or four elements in one iteration, reducing loop control overhead. For example, instead of checking only array of I, we check array of I, comma, array of I plus 1 and array of I plus 2 together in one step. We check all the elements in a single step. In this case also, even though time complexity remains same, this technique improves practical performance by reducing the number of loops execution. And this is one of the best optimization technique introduced till date. Coming to the seventh optimization technique, it is immediate break technique. This immediate break technique ensures that the search stops as soon as the target element is found. Instead of continuing the loop unnecessarily, the algorithm exits immediately using a break statement. In some implementations, the programmers use extra flags or allow the loop to continue even after finding the element. This causes unnecessary comparisons. For example, one target is matched at a certain index. The loop terminates that instantly without checking remaining elements. Although this does not change time complexity, it avoids extra operations and makes the code cleaner and slightly more efficient. So this immediate break technique mostly works on the break statement. Coming to the eighth optimization, which is cache-friendly access. Cache-friendly access takes advantage of how modern computers use CPU cache memory. When elements are stored and accessed sequentially, the processor can load nearby elements into cache, making access faster. Linear search naturally follows sequential memory access, which improves spatial locality and reduces memory access time. For example, when searching through a large array stored in a contiguous memory, it accesses all elements one after another. It allows the CPU to fetch them efficiently. Although the time complexity remains the same, cache-friendly access improves real-world performance, especially for large data sets. And the ninth optimization technique is index memory technique. This index memory technique improves the performance by remembering the position of recently found elements. Instead of always starting the search from the beginning, the algorithm can begin near the last known position. This is useful in cases where same elements are searched repeatedly or when data access patterns are predictable. For example, if an element was previously found at index 6, the next search for the same element can start near the index instead of index 0. Also, the worst case time complexity remains 0 of n. This approaches improves average performance in repeated or localized search scenarios. And the final optimization technique is hybrid approach. The hybrid approach combines linear search with other searching techniques to improve overall efficiency. Instead of depending only on basic linear search, it adapts based on nature and structure of data. This makes searching process more flexible and suitable for differently different real-world situations. For example, if the data becomes partially stuttered, linear search can be combined with binary search. In cases of frequent lookups, hashing techniques can be used alongside linear search. This flexible approach allows the algorithm to adapt depending on data size and the structure. Although the worst case time complexity of linear search remains same, hybrid strategies significantly improve practical performance in real-world applications. Coming to the conclusion, linear search is very simple and easy to implement searching algorithm that works well for small or unsorted data sets. However, its main limitation is the time complexity, due to sequential comparisons and for large datasets. The optimization techniques which we discussed, such as Sentinel, move to front, transposition, two-way search, and hybrid approach, help reduce unnecessary comparisons and improve practical performance. Even though the worst case complexity remains same. These methods significantly improve average case efficiency in real-world applications and give the user the best experience. Thank you.